Hi, this is another video in my ongoing series about documenting the differences between the language Hopper and the other more popular, more common, more well-known curly brace and semicolon languages, especially the modern ones like C# and Java. But if you have familiarity with C++ or C, this will also seem familiar. In a previous video, I used a utility method, a try-parse method, as an example of how to use a reference argument. And it then occurred to me that I was using code from the compiler, which really belonged in the system library. But I'm revisiting that now from a different perspective. And that is sort of a naming convention that is not exactly accurate. So if you look at what I do here with screen print line, that sort of thing, common hello world, build that and run it. It looks a lot like what in Java or C# you see console write line. And in that case, console is an object and write line is a static method on the object. And hence this convention. And you can disambiguate between multiple write lines in your system. So if you've got a write line to write to files or to your serial port or whatever, you can qualify which write line you mean by using the name of the object. In the case of Hopper, it's not the name of an object. It's the name of the unit, which is more like a namespace in C# or Java. But we don't have any objects in Hopper. So it's kind of more or less merged into the same kind of thing, so that your print is qualified by your namespace, and it looks like an object name, but it's actually the unit name. Right. So in going back to the one I was talking about earlier, if we had a string, which is our number value, which is 10, and now we want to get it into a uint, so we've got an unsigned integer. We can go if try parse the number and a reference argument to our uint, and we'll use that same thing we were doing earlier, where we just do println failed here. Otherwise, we had success, and we can just convert it back and see the output. So in the case of success, we just do toString, because I want to use that later. No matching overload. So it's gotten confused by which try-parse I mean now, because I've moved them into the system function. So it thinks I'm trying to call the int one on a uint. So we can disambiguate by putting uint in front like that. There we go. And we've got our 10. So it's calling the try-parse in the uint namespace. So let's go have a look at it. So there's the uint namespace or unit, and here's try-parse. And I took the liberty of also putting in the hex version and the binary version, which used to be separate methods, but I've made them private now, they're lowercase, so that we can make this more interesting. So you can go put a hex number in, and 10 in hex would be 16. And there it is, 16. Or we can make it the binary version. And 10 in binary would be 2. Actually, it wouldn't be 2. Yes, it is. In binary, it's 2. In hex, it would be 8. But it's binary. Okay. Anyway. I extended this. I moved them to the system library where they belong, out of the compiler, so they don't belong in the compiler. But now there's something else in this program that is not quite right, and it's this. So I converted this uint to a string by pretending that it was an object that had a method called toString. Sneaky. Why does that work? Well, it's actually just sort of a syntax sugar for saying uint and passing it as an argument. So if I run that, I get 10, same thing. So it's just a convenience, but how does it work? Why could I do that? Why could I take something that was essentially a value type? Well, even our reference types would do this. We do it with strings all the time. Why does that work? Well, let's go see how that's defined. So if we go and look for the toString for uints, there it is. It has an argument called this, which is actually something special for the compiler. So the compiler figures out that if a method has a first argument called this, and the type of the argument is the same as the unit it's in, and there's another sneaky trick, is that all the types and units have a name which corresponds to their lowercase version. C# does something similar where you can use string and you can use an uppercase version of string like that interchangeably. So I'm doing something similar. It's just a shortcut, is to say if the first argument of the method is actually called this, like the word this is special, and the type is the same as the unit it's in, then it can be used in this special way. It can be used as the syntax shortcut. So if we go and have a look at strings, we'll see a lot of this. Or let's look at lists. They're kind of interesting because they've got some other syntax shortcuts in them. So a lot of the time, the first argument of a list method is this, and it has another abbreviation, another sneaky thing that the compiler thinks is special, which is like a placeholder type. This is like templates in C++. So there's a special template method meaning for v, which basically means it's the value type of this list, which we don't know when we're defining all these methods. So if you've got a list of strings, then the v is a string type. If you've got a list of uints, then the v is a uint. Dictionaries are similar. So if we go and look at dictionaries, they've got two template types, a key and a value. And those two things get used as templates for when you make a dictionary, let's say, where the key is a string and the value is another list or something. They get substituted for these. And this type is here again too. So let's go and play with one of these and see what it looks like in an example. So let's make a dictionary, and we can have a dictionary of a list of strings. There's our dictionary, right? We've got a list of strings. So let's make ourselves a list of strings. And let's add to our list of strings. We'll add some things to it. 1, 2, 3. And then to our dictionary, let's insert that list into the dictionary. And we'll put it in a first time. Now, I also mentioned earlier that we do a copy on assignment, and I can prove that by going list remove 0 at this point, and then put it in a second time. So the second list should be shorter by now, because the original got copied into first, then we removed the first element of the original, and we put it into second. So let's output this. Let's first make sure I haven't made any mistakes yet. Yeah, there we go. And now we go for each var kv can be called anything. I just called it kv because I know what it is. So I'm stepping through each key value pair in the dictionary, and the key value pairs. So they're both string. The first one's a string. So we can println that we're in which dictionary are we in? KV key. Let's see what we get if that compiles. Yes. So let's go there. So we're the first dictionary, second dictionary. First element entry in the dictionary, second entry in the dictionary. Let's have a look at that in the source code again. So the first key and the second key, key and key, right? Now, we're going to just make life simpler here. So we're going to take out list value is the KV value, right? So we pull out the list from the first entry and the list from the second entry. So this list here that was copied in the second one. So now we'll go through those for each var v in LV, for each value in the list, println, and we'll indent it a little bit so that it makes it easier to see, and we'll print it out like that. Let's see what we get. So I expect to see 1, 2, 3 in the first list and 2, 3 in the second list because I removed 1. So let's have a look. There we go. So 1, 2, 3 for the first list and 2, 3 for the second. Right. So a dictionary of lists. You can do this endlessly. You know, list of dictionary of lists of whatever. You can merge them like this, and they're all anonymous types like this. You can't name the type. Anyway, now let's mess with the syntax and make it look worse. So this is that this syntax. So we should just be able to put the word list there, which is the name of the unit that lists are in, and now we can put this as the first argument. So that's just removing that syntax sugar that was kind of convenient to use and looked a lot like C#, even though we don't have objects. And yeah, get the same result. So that's a little bit of the syntax sugar removed. This is also just syntax sugar. So if we go and look at the dictionary, it must have a way of adding to the dictionary. There it is. It's called the set method. So let's go and use the set method instead. So if we go, if we want to, we can change that to dictionary.set. The dictionary variable first is, and if we look at it, it'll be this here, and then so here's set, this, key, and value. Let's go do that. So there's the this, there's our key, and there's our value. Right? And the second one, yeah, and for the list remove, we can go list dot remove list, comma 0. Build that. I made a typo. And get over there and run it. Same results, okay? Just a little bit more longhand in terms of writing. So you get the idea of why we would want to use this syntax sugar to make things look prettier and make it easier to, less to write, and it's easy to understand looking at it. It makes sense. So you don't have to have dictionary and dict there. So it's definitely a lot more compact to just do that. A lot more compact. Or just to move the this and replace the unit name with the variable name and remove the this argument just like that. And then we run it again and we have the same results. So that's what this means in Hopper, even though Hopper doesn't have objects, which means it shouldn't really have a this pointer. And it sort of overlaps the functionality of a namespace and a type to get this syntax to work and to make it look familiar. And so strings behave almost exactly the same way, and so do lists and dictionaries. But you can do it with your own types too. So you can create your own types and use the same convention, and it'll work. Anyway, thank you for watching.